Hello ladies and gentlemen, welcome to my lecture series Modern Gravitational Theory. My name is Genis, I'm a physicist, I work in this field, and to follow the lectures you must have the knowledge of the basic lectures in theoretical physics, the special theory of relativity, and you must be familiar with calculus and linear algebra in mathematics. This is lecture 1, Introduction to Curved Spaces. In classical physics, that means Newtonian mechanics, gravitation is described as a classical field, while in modern gravitational theory, gravitation is described by Riemannian spaces, that means curved spaces. Bernard Riemann was a student of Carl Friedrich Gauss, and Gauss possibly was the very first who was thinking about curved spaces. He had to do with measurements on the surface of the Earth, and the surface of the Earth is, we can say, a curved two-dimensional space. And so Riemann worked that out later mathematically, and so that spaces are called Riemannian spaces. Now, transformations from one coordinate system into another one are very important. So we want to consider a very simple example. We consider a two-dimensional space and want to transform Cartesian coordinates into polar coordinates. So here in the diagram, the polar coordinates are red, r and phi. So to calculate r out of the Cartesian coordinates, we have to apply the Pythagorean rule. Means the square of r is the sum of the squares x and y, because we have a rectangular triangle here. And then phi, to calculate phi we consider the two legs of the triangle. Y is the opposite leg, x is the adjacent leg. So y divided by x is a tangent of phi. And okay, we don't want to have the tangent, we want to have the angle itself. So arcus tangent of y divided by x gives the phi coordinate. So if we want to have the transformation in the other direction, then okay, x, if we consider x is the adjacent leg to phi, that means we have to use the cosine. So r multiplied by cosine phi is the x coordinate, and y is the opposite leg, so we have to use the sine function. R multiplied by the sine phi is the second coordinate, the y coordinate. To characterize a transformation, we use a Jacobian determinant, J, or it's also called a functional determinant. And yeah, it shows the transformation of a vector from one coordinate system into another one. And we can calculate the determinant by calculating the differential quotient of the coordinates. So yeah, if we consider here the first values, we have here x differentiated with respect to r. That means, okay, if we differentiate here, then r is skipped and cosine phi remains. This is the first value here. And the second differential quotient, means x differentiated with respect to phi, means, okay, r counts as a constant factor, and the differentiation of the cosine is minus sine. Though we have minus r sine phi here, yeah, and so on. And so we have the complete determinant here. If we calculate the determinant, then yeah, in the main diagonal we have cosine multiplied by cosine and r. That's the first addend here. And the other diagonal, yeah, that gives us the second addend here. And okay, cosine squared plus sine squared is 1. So the result is r. And if we consider an infinitesimal area element, dA here, then in Cartesian coordinates, very easy, that's the product of dx and dy. And in polar coordinates, yeah, we have to write to the differentials the Jacobian determinant. So that's the value r. And yeah, we have to recognize here an area has got the dimension of a length squared. And phi isn't a length, it's an angle. So we need r as a second length as a proportional factor. And so we have the area element here in polar coordinates by the product r dr d phi. And yeah, if we consider the transformation of a vector dr d phi, means from polar coordinates into Cartesian coordinates, then yeah, we have to apply the Jacobian matrix here, or either written like this. And the line element is given. Yeah, we have to apply the Pythagorean rule. Means ds squared is dx squared plus dy squared in Cartesian coordinates, and of course we have dr squared plus r squared and d phi squared in polar coordinates. Okay. The example of a coordinate transformation we have considered was an example in flat in Euclidean space. So, but now we have to go over to curved so-called Riemannian spaces. So here we will consider only 2- and 3-dimensional spaces at the beginning to keep it very easy for the students. Here we have a 2-dimensional uncurved space, a plane in Euclidean spaces, and here we have a curved 2-dimensional space. The surface of a ball or a planet is, we can say, a 2-dimensional curved space. If we consider the sum of the angles of a triangle in Euclidean space, then the sum of the angles will be 180 degrees always. If we consider a curved space, then the sum of the angles depends on the kind of curvature. If we have a convex curvature like here, the surface of a ball, then the sum of the angles in a triangle would be bigger than 180 degrees. And if we have a concave space, then the sum will be smaller than 180. Okay. A space can be described mathematically by considering the distances between two arbitrary points which are infinitesimally close together. So we have to apply the Pythagorean theorem again. Means the length, infinitesimal length ds squared is the sum of x and y squared. So we have here a normal Cartesian coordinate system, and we have here the length ds. ds is naturally given, and if we want to describe something mathematically, we put a coordinate system, an artificial coordinate system, into the problem to make a mathematical description. So here we have an uncurved Cartesian coordinate system to describe ds. In the second example here, we have a curved coordinate system, 2-dimensional curved coordinate system. ds is the same ds like here. It is in nature given ds, and we put an artificial coordinate system into the problem to make a mathematical description. Okay, and that is clear. The length ds is the same. It doesn't depend on the coordinate system we put into the problem. And this principle should be known from the special theory of relativity. If we make a transformation, the line element ds, the four-dimensional line element ds, is unchanged in the conservation quantity. And though we now consider a vector or vector space in the flat space and in a curved space. We suppose a vector A. In the Cartesian coordinates, the three axes shall be x1, x2, x3. And we have a vector A at each point in the space. And so we can write with the three components that should be known. The three components are A1, A2, A3. And now in the curved space, curved three-dimensional space, the same vector now is described in the same way, but the values A, the components, are other values. So we write it with a prime here, and the basis vectors are also other vectors. We call them G, G1, G2, G3. And the coordinate axes here are y1, y2, y3. Okay, and now that should be known in a curved coordinate system or curved coordinate lines. The G vectors are tangent vectors to the curved lines. And so we have to differentiate the x components with respect to the y components in the curved system to get the new basis vectors gi. Means the three x coordinates must be differentiated with respect to y. If we calculate g1, then we have to write here y1 and so on. Okay, and a vector is the same vector in the uncurved and curved coordinate system, but it's the same vector, so we can write this equation here, 13. And now we want to calculate the scalar products with the basis vectors e1, e2, e3, and we use 12, the expression for the g vectors. So if we multiply 13 by e1, then we have to know that the scalar product of two orthonormal basis vectors is 1 if the indices are equal, but the product vanishes if the indices are unequal. Okay, and so that means the second and third addend here vanish because the indices of the e vectors are unequal. Only the first addend gives a value, because e1 multiplied by e1 is 1, and so only a1, the component a1, remains here on the left hand side of the equation. Then on the right hand side we put in for the g vector, this expression is sum of 3 addends 3 times. Okay, and now we multiply by e1, and here the same. In every big term here, the second and third addend vanishes because unequal indices, and only the first one remains in the equation. So, and though that gives for a1 this equation here, 17. And in analogy, we can calculate the other two components, A2 and A3. Okay, then we have the three equations. The difference is in the first line we have x1 in the numerator, then here x2 in the second and x3 in the third line. We can also write this with vectors and a transformation matrix. So we have here the vector of A1, A2, A3, and here the vector with the primed coordinates, and here the matrix with all the differential quotients. Or we can write it shorter like this. A vector is equal to M matrix multiplied by A primed vector. The inverse transformation can be obtained by using the inverse transformation matrix, that is M minus 1. We can imagine we multiply equation 20 by M minus 1 from the left. So that means the left side here would be here the right side of the equation. And that's clear. Matrix multiplied by the inverse matrix, that's the unity matrix, neutral element of the matrix multiplication. So we have here the inverse transformation. Okay. Now we want to calculate the gradient in curved coordinates. So that should be clear from elementary mathematics or elementary theoretical physics. The gradient of a scalar field phi can also be represented by the nabla operator, and there we have to differentiate the function with respect to the coordinates x1, x2, x3. Here we are in the Euclidean space, and then we get the three components of a vector. That means we have then a vector field to the scalar field, and the vector gives us the direction and the value of the greatest change of the scalar field. And we can write this as a scalar product of two vectors. Here the row vectors with the differential quotients and the column vector with the basis vectors. So now to get the basis vectors in the curved space G1, G2, G3, we use a transformation matrix M, but here we have to write the transposed one because we have to look at here in 12 we see the G coordinates are the X coordinates are in a row x1, x2, x3, and so we have here x1, x2, x3 in a column, and so columns and rows are exchanged, and so we have to use here the transposed M matrix. Or in the other direction, then we have to use the inverse matrix of the transposed M, and so we can transform the vector with the G vectors into the vector with the E vectors. Okay. Then, because we want to know the gradient in the curved coordinates, and so we use here the chain rule of the differentiation. That should be clear from calculus. Now we want to differentiate to the y coordinates. Okay, we have three y coordinates, so if we apply the chain rule here, we get a sum of three addends, y1, y2, y3. Okay, that should be clear from elementary calculus. And if we calculate the other two equations, then we can write this as a vector equation. Here we have then as a vector on the left hand side, the differential quotients with respect to x, to the x coordinates, and then we write a transformation matrix, and here we have the vector with the differential quotients with respect to the y coordinates. Here we have to write a new matrix n because it hasn't anything to do with the M matrix. In the M matrix we had the x coordinates in the numerator and the y coordinates in the denominator. And here it is vice versa. We have the y coordinates in the numerator and the x coordinates in the denominator. It's another matrix then. Okay. Then we substitute in the expression for the gradient in the Euclidean space and write for the it was a row vector with the differential quotients with respect to the x coordinates, and so we have to write not this, but we have to write the transposed one of this, and we exchange the vector with the e vectors by this expression with the g vectors, the basis vectors in the curved space. Okay. If we transpose this now, then we have the row vector instead of the column vector, and that should be clear from linear algebra. If we transpose this, then the matrix is written at the right side like this. Okay. And now here we have a product of 4 factors, 2 matrices, a column vector, a row vector, and the multiplication of matrices is associative but not commutative. So in which order we execute the multiplications, that makes no difference, but we may not change the order. So we first want to calculate the product of the 2 matrices here. Okay, but we start to calculate the product M and N transposed. So if we write this down here and execute the multiplication, then here we have a new matrix with only differential quotients with the x coordinates. And okay, that should be clear. Such a differential quotient is 1 if the indices are equal and is 0 if the indices are unequal. Okay. And so here we have only in the diagonal, main diagonal, equal indices. So that means we get the unity matrix, one matrix, and so we can multiply this with the inverse of mt by the right hand side, and then we have n is equal mt minus 1, and so we can write instead of this mt minus 1 here n. Okay, so we have this expression for the gradient, and now if the n matrix is applied to this vector, and then the result is a new vector, and n transposed is applied to the new vector, we get another vector, and then we call this new vector g primed, and then we can write this, and so this expression here defines a new vector with new basis vectors g1 prime, g2 prime, g3 prime. So then we can write for the gradient in the curved space, yeah, this expression here, we see it's exactly the same shape like the gradient in Cartesian coordinates, but we differentiate now with respect to the y coordinates, and we have of course the basis vectors g prime in the curved space. Okay. Now we finished lecture 1. Next time in lecture 2 we will look at the concept of co- and contravariant coordinates. Very important. Thank you for watching. See you next time. Goodbye.